I hope the mic is working. So I guess that means I have to say, go blue, right? Because, and there's a football game later today, don't forget. I have my ticket right here. So I'd like to tell you a little bit about some of the puzzles that I've been thinking about. I wish I could say since undergraduate, because a lot of this has to do with problems that come from aerospace engineering and other fields of engineering, but that's not true. I thought I was going to study fluid dynamics and control theory when I went into graduate school, but as is usually the case, I didn't really know what I wanted, and I just chose an advisor that I thought would do me well, and he steered me towards these kinds of problems I'm going to tell you about today. So I want to start by just telling you what, in a few pictures and words, a thin elastic sheet is. There are two words that I just want to kind of tell you about here. One of them is thin, and we'll make that quantitative in a second. The other one is elastic. Now, elastic, you could think springs, you could think some sorts of polymers. The kinds of materials that you're seeing in front of you are varied and all have the feature that when you deform them by loading by a point force of various sorts or by internal depressurization, they spring back to their original shape. That's an elastic solid. And what makes these thin is that if I measure their relative thickness, which in each of these pictures is roughly 10 to the minus 4, okay, so how do you do that? That's a beach ball. So you cut out a piece of that beach ball and you say, how thin is that in dimensional units? You measure it, that's T, and then you ask how big is its diameter? That's your lateral length, L, and if you divide those, that gives you a non-dimensional number, which is going to be rather small for a beach ball, 10 to the minus 4. And the fact that this number is small is, so somebody like me, going to indicate that if I force this in some way by loading it with a point force, it's going to wrinkle or crumple or form some other kind of small-scale pattern that I'd like to figure out. So these are two different experiments that are similar to each other in that they both start with thin elastic sheets and they're both loaded by a point force. And there's a key difference between them. One of them is exhibiting wrinkling patterns that somehow remember that it started out as a radially symmetric shape, a sphere. But this one is internally pressurized, and the pressure acts as a restoring force. That causes wrinkles to happen, apparently. This one, there's no restoring forces that are distributed like pressure would be, but rather there are restoring forces coming from the tabletop that it's sitting on. And when you poke it like that, you see a folding pattern that emerges. Actually, something really interesting is happening. If you poke it just a little bit, you see a radially symmetric response, kind of akin to the balloon. And if you poke it enough, you see that it loses its radial symmetry altogether, folds instead. This one, I think, is the most striking image on the slide, and an experiment that I'd like to understand better than I do now. What's happening is this is a nickel alloy, which is thin, 10 to the minus 4 thickness, relative thickness. And it's been depressurized from the inside. So you can see that there's a little pipe coming from the right, and you very slowly take out the air from the inside, and it responds by forming this beautiful tiling pattern of the sphere. You know, hexagons tile the plane, but hexagons can't tile the sphere. There have to be defects, and if you look very carefully, you can see there are some pentagons that appear before your eyes. But the interesting thing that's happening here is that it's not clear that when I start with a thin elastic sheet and I depressurize it from the inside, I should see wrinkling patterns that are solving a geometry problem, a tiling problem. That's not clear at all. And as a mathematician, I think, and a physicist and an engineer, I think the interesting question is, well, why is that happening? And is that a general fact? Are there always geometry problems behind the shapes that you're seeing? So here's a few other ones. So paper, crumple up a sheet of paper, that's an example of a thin elastic sheet that you've loaded in some way. And here's another experiment we'll get into later on in the talk, and we'll do that in detail. This is a floating this is a floating polystyrene, so that's a polymer substance, a polystyrene sheet. This is the thinnest one that's shown on the slide at relative thickness 10 to the minus 6. Anyways, the point I'm trying to make is that your experience with crumpling paper can help you understand the kinds of patterns that you're going to see at larger or smaller thicknesses, and they're all governed in these many different orders of magnitude of thickness. They're all governed by elasticity. Okay, so I have to warn you, my wife didn't want me to show the next slide. If you're afraid of flying, you should look away. So, but this is an old joke I learned when I was an aerospace engineer. If it's going to load. My computer's trying to prevent me from telling you this. Okay. So is that a thin elastic sheet? So that's a Boeing 747, and it's made up of, well, none of the substances I showed you before, but something more like steel. These days it would be made up of a composite material, but nevertheless you could imagine that if you cut out a little section of that fuselage and you deformed it and you let it go, it would spring back to its original shape. Surely hope so, right? What about its thickness? How thin is that? As thin as paper. So, okay, so I'm playing a little bit of a trick on you. It's not like you're flying up there in a paper tube. Actually, if you look at the side of it, it's more like corrugated cardboard. Okay, all right. So maybe you feel better. I like to leave politics out of my talks, but just one slide about that. So I think basic science leads to future engineering, and that's why you should fund basic science, one of the reasons. Well, but actually not even just the future. Look at these pictures over here on the right. These are architectural renditions of folding patterns that you might want to design. Those exist already. This is a folding pattern in nature. And the future engineering problem is, well, if nature finds a way to use folding to unfurl a leaf, could you design buildings or structures that reconfigure themselves at will by choosing the right kind of folding pattern? So I guess the message I'm trying to tell you here is that elastic patterns can be used to drive shape change, but overall shape change. But of course, before we can get to the point where we can use the patterns to change the shape of the object, we better understand the patterns first. That's the basic science question. So here's the question I want to chew on for the rest of the talk. Which patterns emerge from confining forces or confinement? There's one thing that's sort of the same between all of these pictures, some of which hopefully all of which you recognize, which is that every experiment involves compression. There's no stretching being done. If I take a thin elastic sheet and I stretch it taut, it's very easy to say what it's going to do, right? We all have experience with rubber bands. That's sort of a stable deformation. If I take a sheet of paper and I stretch it, it doesn't like to do anything, but just retain its original shape. But if I compress it and crumple it, then I get a wild mess of folds that emerge, and that's the puzzle. Can you figure out from confining forces what selects this kind of pattern as opposed to another orderly pattern such as this one? This is a folding pattern that has the same effect where it starts out as a flat sheet of paper and it folds into a much smaller area. In fact, this one folds completely flat. This is called a Mira-Ori pattern, and you get the feeling that this is just sort of a disordered or random version of this, but we haven't quite put our finger on whether or not that's true. Okay, so let's do the basic science. So the rest of my talk is going to be about the essentials of thin elastic sheets, which I'm going to start with next. I'm just going to tell you a little bit about the three basic forces that are involved in each of these experiments. And then we're going to apply these ideas to talk about crumpling and origami, which I know not too much about. And then we're going to talk about wrinkling of shells, and that one I can tell you a lot about. So hopefully that'll be a lot of fun. So the first kind of force that I want to tell you about is called the stretching force. And I guess this is this is actually quite familiar, hopefully, and most easily demonstrated by telling you about something called Hooke's law. So this is an old idea from physics due to Hooke, which says that if I have a spring, so that's kind of an elastic material, right? If If I deform it and then let go, it goes back to its original position. And anyways, if I want to figure out the amount of displacement that occurs when I place a weight onto the spring, I can do that experimentally, right? So I can do this, and I can see that when I put a certain amount of weight onto, a certain amount of force onto the spring, it displaces in units of 2 displacement units for this spring, okay? And if I put another block on there, so I double the amount of force, then it's going to double the displacement. After it loses its energy, it has to settle down a little bit. So what we just learned is that from this simple experiment, and this is what Hooke discovered, that if you load an object with twice the force, then you get twice the displacement, twice the change in length. And the proportionality constant K, which depends on the properties of the spring, depends on what it's made up of, depends on how long it is, that's going to be Hooke's constant K. Something that maybe is a little less familiar than Hooke's law is the energy involved in displacing the spring. So if you think about how much work or energy you have to expend to displace that spring, you can figure it out from Hooke's law, and I'm not going to do that now, but what you get out is this law. You get that the energy required to displace a spring by a certain displacement delta L goes like the square of delta L. That's a familiar result from springs. And with this prefactor, which is 1/2 the original spring constant. So the upshot is you make your spring, you measure the spring constant, then you know how much energy you have to spend to deform it. Okay, so stretching forces work in a similar way for thin elastic sheets. Thin elastic sheets are not simply made up of single springs. They're more like this. They're more like a bunch of springs that are put together in sort of to make a sheet. And if I load that spring assembly, then all of the springs resist me all at once. And when I let go, it springs back to its original shape. So that's how I know that it's elastic. And so anyways, if I think about dividing the rubber block or the sheet of paper or whatever up into lots of tiny little springs, I can figure out that the energy required to stretch the object, that is to say, the energy required to take this sheet of paper and stretch it, which as you know is enormously large. I'm never going to actually be able to stretch this, right? Goes like 1/2 times a constant times the strain squared. Okay, so thin sheets don't like to be strained, just like you and me. So what's strain? Strain is change in length relative to original length. So this is like the delta L from before. This is just like this, but relative to the original lengths of the object. Y is the version of Hooke's constant, but for the thin elastic sheet, and sort of that's how it works. So there's a nice mathematical concept behind the idea that thin elastic sheets like to deform in such a way that they undergo no strain. If I try to make the stretching energy as little as possible, I'll do so if I deform the sheet so that all of its lengths in its original shape are the same as all of its lengths in its final shape, so that it's not in a state of strain. And that is the word isometry, isometric, same lengths. And what's going on in this experiment, so I think now is probably the time to explain that, is that you take, if we could just look at this here, you take a mylar, so this one is mylar, but, okay, so this is a mylar sheet floating on top of a water bath, and the experiment is polystyrene, so it's much thinner. So you take a thin elastic sheet and float it on top of a water bath, and you see that it floats there by itself. We'll get into that in just a moment. But then you take 2 blocks, and you go to the left and the right, and you ever so slightly compress them together. Now this is a rather thick elastic sheet, so I have to be very careful when I'm compressing it, because if I compress it too much, then it's gonna sink. But you can see that when I compress it, it sort of buckles. It forms a wrinkle. And you could imagine that if the sheet was much, much thinner than the demo that I'm showing you here, such as the one that's shown over there, that's 1 to 300 nanometers thin by 1 centimeter wide, So if the sheet's much, much thinner, then when you compress it from the left and the right, it'll not sink, it'll not buckle in the way that this one does, but will rather form a much finer wrinkle pattern that looks like a curtain that's draped from your windowsill. Okay, so what about isometry? So the point is that when you measure the rest length of the distance between any 2 points in the object at rest, and then you go to the deformed picture and you look at this, and if you measure then the length of any curve that results from the deformation, such as the one that's oscillating up and down, as you can see to your eye, it will have the same length as it did in the rest state. So all lengths are preserved, and that tells you something about the kinds of patterns that you can see. You can't see any pattern. You have to see patterns that preserve the lengths of the original object. Okay, so much for stretching energy. The next part is bending energy. So bending energy is the energy that you have to expend to bend an object like this. So whereas I can't stretch a sheet of paper, that's very hard to do, I can very easily bend a sheet of paper. So you see that, so we've already learned something. If there's a Hooke's constant associated with bending, it has to be much smaller than the Hooke's constant associated with stretching. And indeed, there's such a thing. It's called the bending modulus B. The law for bending energy is that when you curve an object by a certain amount, then the energy you spend goes like the square of the amount by which you've curved it, and the proportionality factor, that's like the Hooke's law, is called the bending modulus B. B is much, much smaller, orders of magnitude smaller than Y. That's why it's so much easier to bend thin sheets than it is to stretch them. So this is undergoing quite a lot of bending. Okay, so there's got to be energy stored in that. There's another source of energy in this experiment. It's the gravitational energy of the water bath that the thin sheet is floating on top of. When you know that there's such a thing called buoyancy. When you stick your fist into water, it displaces the water by a certain volume, and the amount of work that you have to do to displace that water is proportional to that volume. So when the sheet wrinkles, it's also displacing water up and down, and that displacement is resisted. Can we just bring this up very quickly? This takes a lot longer than I expected. Okay, so see how when I poke it, it springs back to its original shape? So that's the buoyancy forces that are restoring it back its original shape. When I poke it like this, I have to expend work to do that. I have to expend energy. Okay, so and so you can imagine that this matters when you're trying to figure out the patterns that you're going to see in this simple experiment where you're floating elastic sheet and you're compressing it from the left and the right. Okay, so the upshot of all of this is that you can figure out the pattern that you're going to see, the wavelength of the wrinkles, if you wish, by minimizing or balancing the energy that you expend on curving the object and against the energy that you spend on displacing the water. So I'm just going to step very quickly through that in a diagram to show you what that looks like. The goal here is to predict the length scale of the wrinkles that appeared before our eyes. So this, if I look at the wrinkle pattern from the side view, I could imagine, this is not what you see in the experiment, but you could imagine that you see a big bump like this. And if you have a big bump like this, it's going to have not too much curvature, but it will have a lot of amplitude. And that has a certain energy associated with it. And then you imagine, well, what if I had a few bumps, but in such a way that the total length of this curve was the same as the length of the original curve? Because sheets like to preserve their lengths. Well, then that's going to have a different amount of energy associated with it. And you can step through all of these possibilities, and one of them has the least amount of energy. And the basic model in this area says that to determine the patterns, one should minimize the total energy, the total potential energy stored in the system in order to determine the length scale of the patterns and the patterns themselves. So what comes out of this analysis is that this length scale is the preferred one. Okay, so They told me not to do too much math in this talk, so that was it. So if you go through and you do the math, you find out that, well, okay, so if you know a little calculus, you got to minimize this in the choice of L. So you do that, and you get out a law that says that the length scales should be like the fourth root of the density of the water times gravitational constant divided by the bending modulus. Okay, and then you go and you plot this against lots of experiments to figure out whether or not that's right. And here you're seeing the prediction here from the analysis we just did together plotted as this curve, and there are many experiments where you measure the wavelength as you're seeing here, and you see that they lie indeed right on top of that curve. So this is something that we can take to the bank. We know that the wavelength of Wrinkles is predicted by minimizing the total potential energy in the system, and that's that. Okay, so those are the essentials, except for that there's one question left undescribed in this simple analysis, which is what is going on near the edge. You can see that the wavelength is not constant, like I predicted it to be, but changes from point to point. Like if you hang a drape or a curtain from your wall, the wavelength can also change from height to height. And that's just because there's a meniscus at the edge. And what I should do to figure out what the length scale of wrinkling at the edge is balance the meniscus forces against the bending forces. And if I do that, I'll get a different prediction for wavelength than if I balance the buoyancy forces against the bending forces. Okay. So now we have some interactive. So let's all roll up our sleeves. Let's try this together. There was a physics review letter about this published recently. So if you think that physicists are stuffy, no. Roll up your sleeve. So everybody rolls up their sleeve, and you see an interesting pattern that emerges, right? Okay, so what could determine that pattern? So that's a thin elastic sheet, and you know that the kind of deformation that happens has to preserve all the lengths of the original sheet. Now, if your clothes are tight-fitting, you'll get a different pattern than if your clothes are loosely fitting. But anyways, in this simple tabletop or experiment that anybody can do, you'll see that there are stretching forces, there are bending forces, there are confinement forces, and you have to settle all of that to figure out the patterns that you see when you roll up your sleeve. Okay, good. Let's move on to crumpling and origami. Okay, so now we're going to ask, so we did the basic question of figuring out the wavelength of Wrinkles, and we saw we had to minimize total energy. So now I'm going to ask the more serious question, or fun question, which is, how do you determine that? Okay, so I guess, well, I don't know. That's a really hard question. That's like asking, how does glass break when you break it? I put a bunch of energy into the system, and it decided that rather than spreading it evenly throughout the sheet, it would concentrate it onto a network of folds. And what network is that? I'd be hard-pressed to say. But I can ask as a mathematician, I can ask the question, if I crumpled the paper, how much energy did that take? That's a well-defined question. And I can try to sort out the answer to that. Now, that's going to depend on the random network of folds and ridges that you end up seeing in any one particular instance of crumpling. That's, of course, why this is such a hard question to study, because you don't know the crumples that are going to emerge in advance. But let's ask the following question. When you crumple a sheet of paper into a certain size, okay, into a certain size or volume, do you spend more or less energy than you spend when you fold up that same sheet of paper into that same volume by origami folds? It's reasonable. I mean, so you see that there are two different ways to pack the same amount of material into the same small confined space, but it's reasonable to imagine that the amount of energy you expend in doing this one is much less than the amount of energy you expend in doing this one. Of course, you have to plan a lot more, right? You have to. That's where the energy went. You have to plan a lot more to make this one happen, okay? But when you actually do the experiment and you crumple the pre-designed folding pattern that we have right here, you'll see that it can go from being a flat sheet down to one that is much smaller than its original size. And if I choose different folding patterns, all that's happened here is that the angles of the folds have been changed. It's the same quadrilateral mesh, if you wish, but the angles have been changed. And if I crumple that down, then that can fold even smaller. So, but nevertheless, it seems like it takes a lot less effort to do that crumpling than to make this happen. And this one is predictable. If I crumple it over and over again, it'll fold on the same lines. And if I crumple up 2 sheets of paper, I'll get something different every single time. Okay. That's kind of a workout, actually. So that's the math question. That's the math question. Is origami the most efficient way to pack material into a given space? So you have to pack your suitcase with your clothes. Do you fold them up nicely along pre-designed folds, or do you just wad them all up and throw them in? Okay, so sometimes I wad them all up and throw them in. But most of the times, I like to fold my clothes nice and neat and pack them in this way. And so that's efficient in the sense that you could pack up more material into the same volume if you were to fold along pre-programmed lines. But that's not the kind of efficiency I'm talking about. I'm talking about energetic efficiency. How much work or energy does it require to fold along these pre-programmed creases as opposed to fold up along random lines? Okay, so this is the math question. I give you a volume, your suitcase. I want you to stuff a thin elastic sheet into it. Among all possible ways to stuff that thin elastic sheet into that suitcase, which one has the least amount of energy? All right, so I don't think that John Nash was thinking about that question in the 50s, but here's a way to pack up paper into a suitcase. This is a realization that appeared in PNAS in recent years of a way to pack a thin elastic sheet in a strain-free way, a length-preserving way, isometric way, into a small volume. It's called the Nash isometric embedding. There's a famous story about Nash's isometric embedding, and I'll explain in a moment what's going on in this picture. But there's a famous story about this where it turned out that Nash was challenged to a bet. The bet was this. So we know that we can tell surfaces apart by how they're curved. We know that spheres, which are curved in one way, are different from planes, which are curved in one way, are different from saddles. Saddles like on the saddle of a horse, which are curved in a different way. But let's imagine that I gave you a flat, square sheet like this. So this one is flat, so it has curvature 0, bending energy 0. The question is there a way to take that flat sheet and stuff it into a tiny suitcase, preserving all the lengths in such a way that it looks kind of like this? So step 1, take the sheet and roll it up into a tube. Okay, so I have my nice sheets here. So step 1, roll it up into a tube. Okay, so that rolling action preserved all the lengths of the sheet. I haven't done any stretching energy. I've only done bending energy. Step 2, make a donut out of it. So I'm going to take now the bottom and the top pieces of the sheet, and I'm going to try to glue them together. Now, that's never going to happen with a real sheet. It's going to resist me doing that, right? I'm going to have to try to, here I go. Here I'm trying to glue them together. The real sheet is going to resist me doing that. But if I just think about maps that preserve length, and I don't worry about bending energy, I could try to glue the edges together. Now, it's reasonable to think that that's impossible. That's impossible to do in such a way that all the lengths on the original square are the same as the lengths in the donut, right? Because donuts are curved. And so if I took any 2 points on this square and I connected them up, they would have the same distance between them on the cylinder. But then if I found those 2 points on the donut, I would notice that some lengths on the donut have been stretched and some lengths have been compressed so that I can fit the 2 sides together, right? Okay. But the goal was to pack it into a suitcase. Next step, shrink the donut. So now when I shrink it, so I've taken my this is my thin sheet of paper. I've now made it into a tiny shrunken donut that I can fit into my suitcase. The nice thing about this is that if I shrink it enough, then any of the lengths that mismatch in such a way that they're smaller. This one is totally compressed. It wants to spring back into its original shape if I shrink it enough. And because of that, I'll have an excess of material. I'll have excess material around the donut. And if I let it go, maybe it does that. That's the idea. So this is what happens. So that's the process that you go through to construct this Nash's isometric embedding. And so just to review, I've taken a square. I've identified the left and the right edges. That's this gluing. Then I've identified the top and the bottom edges. That's making it into a donut. Now we have something called the flat torus in mathematics. Flat because it started out flat. I've shrunken it, and then I've taken all the shrunken material and wrinkled it away. And if I do that, Nash told us that you can program the wrinkles. You can choose the wrinkling pattern in such a way that just the right amount of material was wrinkled away, so that the total map that you get going from here to there is isometric and has no strain and preserves all the lengths from the top to the bottom, so that in Nash's mind, the square is the same as the wrinkly donut. Okay. So this is a beautiful and deep and challenging theorem to understand. It took mathematicians decades to understand the arguments that John Nash made when he proved this theorem. In fact, in mathematics, Nash is more famous for this theorem than he is for his Nobel Prize. And so let's just zoom in a little bit and see the structure of the wrinkles that basically what I'm saying is, it could be, this is wild, it could be that when you find the optimal way to crumple a sheet of paper into a small suitcase, you should do this. Could be. Can't rule it out. Okay, so let's zoom in and let's think about that for a second. So if you zoom, so the amazing thing about this embedding is that it's fractal-like, it's self-similar. It looks like itself when you keep zooming in. So if you take this picture here and you zoom into it, and then you zoom in again, you start to see that the wrinkles you're looking at here are happening at length scales. You see sort of the same picture that you saw before, but zoomed in. Now, if you zoom in again, you can see that inside every single one of these corrugations or wrinkles, there are more wrinkles. So this is like a hierarchy of corrugated cardboard glued together in some funny way, where you have big wrinkled pieces and small wrinkled pieces and ever smaller wrinkled pieces, and you glue them all together. And if you do that just right, like Nash described, you can do so in a way that is strain-free. Okay, so I don't know anybody who believes that this is the optimal way to pack a sheet of paper into a suitcase, and that's because we forgot to ask how much bending energy did this cost. So this costs no stretching energy because all the lengths have been preserved in this process. But if I calculate the bending energy that's required to do this, I'll find it's infinitely large. And that's because there's an infinite sequence of wrinkles that have been superimposed on top of each other. And if you add up the bending required to generate that infinite sequence of wrinkles, you'll get an infinite amount in the end. That doesn't stop you from wondering whether or not there is some version of clever packing that looks like an approximation of this. And that's sort of, we can't rule that out. Not yet. Sometimes origami is what we're after. So I want to switch back to origami. So basically I've hopefully convinced you that this question of optimal packing of paper into a suitcase, into a small suitcase is challenging. It's challenging for real mathematical reasons. There are lots of possible answers, ones that you might not guess from the beginning. You could guess that the optimal way to pack into a suitcase is to fold up one of these nice folding patterns, but we can't prove that. We don't know that that's true. But origami is still an interesting thing to study unto itself. So I've just chosen two different pictures from the literature surrounding, credits will come at the end, literature surrounding this field, and I just want to talk to you a little bit about what's going on here. So sometimes when you're studying thin elastic sheets, you want to make origami happen in a controlled way. And on the left, you're seeing an idea of a fellow named Chris Santangelo at University of Massachusetts, Amherst, where the idea is this. You take two polymer sheets and you sandwich a hydrogel between them, something that expands when you heat it up, and you make slits. You make slits in the polymer sheets on the top and the bottom. You can make slits in any way you want, but the idea now is that if I heat up the hydrogel, I heat up the system, it's going to expand, and the slits are there, so it's going to fold in some controlled way. And this is a demonstration of what you can make with that kind of tri-layer system. You can make the world's smallest paper crane. That's 100 micrometers. All right, so I've heard Chris talk about this many times, and each time he tells me that this one doesn't fold itself up. It gets stuck, right? So they have to sort of jostle it as they're heating it up. And when they do that just right, then out comes the paper crane. But you can imagine the future engineering possibilities from these ideas. This one is from a group actually spanning many universities, but one of the authors is Mahadevan at Harvard in the applied math group there. And this one is showing you that it's possible to fold. These all started out as flat sheets, perfectly flat. It's possible to fold in such a way that you get round objects out. So this one, you fold it up and you make it into a sphere. Of course, if I fold it just right, I can fold a cylinder. That's not hard. This is called the Schwartz lantern. Kind of looks like a silly straw. But you could imagine that instead of putting the creases in the diamond pattern that you're seeing here, you could move them around ever so slightly. You could preferentially choose their location, and if you did that, maybe it would fold up into a sphere, or into a saddle, or into something whose curvature changes sign. Okay, so these are three answers that their computer program generated to possible folding patterns to achieve desired shapes. And these are demonstrations that if you follow the sequence of folding rules that their computer program tells you to use, you can indeed fold up those shapes by hand. So sometimes origami is what we're after when we're studying crumpling and packing. But for somebody like me, I think the most interesting thing here is that sometimes origami happens on its own. So I just want to spend a little bit of time thinking about why that's the case. This is the roll up your sleeve experiment. So you're seeing an experiment, which I'll detail in a moment, that before your eyes produces this pattern, this diamond buckling pattern. And so what's going on here? So there's a thin elastic sheet that is starting out as a cylinder. So it's been glued together into a cylinder like this. It's been fit inside a hard metallic rod. There is like your arm. Your arm is the hard rod that's inside and hidden from your view. And then it's been compressed from the top and the bottom. That's like rolling up your sleeve. And when you do that, you see that as you compress, because the hard rod inside is arresting the motion of the thin sheet so that it doesn't go wild to the left and the right, it instead finds this beautiful diamond folding pattern on its own. And if you compress it enough, you can start to see the inside rod appear before your eyes. You can see where some of those diamonds that are beautifully displayed here have started touching the cylindrical rod on the inside, so you know that that's evidence that it's there. And so I think the interesting math question here and physics question is, why is it that this experiment drives the formation of an origami folding pattern? And that's, if I think all the way back to the beginning of the talk, that's like the experiment when we took the thin sphere and we deflated it from the inside, and we found a geometrical tiling problem. Here we're taking a thin cylinder and we're loading it from the top and the bottom, and we're finding a folding problem, an origami problem. And how could it be that the physics of thin elastic sheets produces these geometry problems on their own? Okay. So the last part of the talk, I'm going to pivot and tell you about something that I know a lot about. So crumpling in origami has been explored by quite a few people. There are very few mathematical results. There's a lot of data in experimental data and scaling theories in the physics and engineering communities. And I want to tell you something now about wrinkly shells, where the math, physics, and engineering communities are starting to merge. So our results are starting to become quite similar to each other. Okay, so I'm going to pivot now and I'm going to tell you about this experiment, which I'd like to demo. Okay. Okay, good. So this is not my experiment. This is an experiment that Hure and Biko came up with. The credit will be at the end. So as with all of these experiments in this field, it's something that you could do at home with tabletop materials until you want to do it repeatedly. Then you need an NSF grant. Okay. So this one is going to start out flat. So I'm going to take this mylar. This is mylar, like a mylar balloon. I'm going to take this mylar disc and lay it flat on the table so that you can see that it did start as a flat sheet. So that's the geometry. It knows that it's flat. Now, as I bend it, as we learned, as I bend it, I have to pay energy to bend it and change its shape like this. But the rules are that it's much harder for it to stretch than to bend. So it bends in such a way that all of its lengths are remaining the same, but it's still allowed to bend. So now what I'm going to do is I'm going to place it between two lenses. So let me show you these lenses. So this is a lens, and this is another lens. They're made of plastic, tabletop experiment. And so these ones fit together, and they're known spherical shape. Okay? So spheres are geometrically not the same as flat sheets. That's an old idea from the geometry of surfaces. And I can demonstrate that to you with this experiment by trying to force what was originally a flat disk onto the sphere. So I'm going to do, so you can already see that it's if you could see it from the side, you would see that it's resisting the clamping of the shells together. They're resting at their rest gap size is non-zero. It doesn't like to stamp into a sphere. Now I'm going to force it to stamp by just stamping it. Okay, so as I do that, I see that the wrinkles refine, and I see this beautiful pattern emerge where the wrinkles are not all at the same wavelength. The wavelength changes from radius to radius. They all seem to emerge perpendicularly from the boundary. They vanish in the center. That's the experiment. So let's do other versions of this experiment. So here I started with a mylar disc. I can do a wax paper disc. So once again, it doesn't like to be stamped flat, so it rests at a gap size that is non-zero. And then I force it to stamp flat, and I see this very similar pattern emerge. There's a little too much light. Well, hopefully you can see the, right? Okay, good. Let's move on. So what else can we do? So let's change the shape of the original cutout that we used. So this one's going to be a square. So this one starts as a square, and it's cut out from a flat mylar sheet, and I'm going to stamp it onto a sphere. You know, stamping is actually a process used in engineering to make cars and other curved objects. And you can wonder, when stamping fails, how does it fail? Does it fail in this way, or does it fail because the metal tears apart? Well, anyways, I don't have more to say about that. But you can see that you still see the same kind of wrinkling patterns that you saw in the previous experiment, but they know that it started out with a square. All the wrinkles are emerging perpendicularly from the boundary everywhere, and the length is changing from point to point, the length scale of wrinkling. We can go on and do all sorts of experiments. Let's just do one more. Let's do one more to see what it looks like. Let's do a triangle. Okay, so you can already see the wrinkles are starting to emerge perpendicularly from the boundary, and as I stamp it, their length scale gets smaller and smaller because I'm forcing it into that configuration, and they stay perpendicular to the boundary. And they form this sort of tree-like pattern right here, where you can see the roots of the tree, and then there's sort of the trunk of the tree right there. Okay, good. Back to the slides. So, these are beautiful experiments in this field. I wish I could say I came up with them. But, okay, so we just did the experiment on the left. We did various versions of it. And there's the rod stamping it. This is the reverse experiment. So this one starts out as a curved piece of a sphere. This one starts out as the top half of a ping pong ball. Well, actually, it's made up of polystyrene. So the top half of a floppy ping pong ball. And then it's been laid onto water. You can see that's the schematic here. You lay this very thin. This one is about 150 nanometers thin, relative thicknesses of about 10 to the minus 6. You lay this on top of a water bath, and it starts out being a sphere, and it assumes an approximately planar shape. And the question is, what's the pattern of wrinkles? So, you know, one thing you learn when you study science is in physics and engineering, and a lot of math as well, is that if you ask a radially symmetric problem, if your problem doesn't depend on rotations, and you could rotate the original configuration and ask the same question, the answer should also be radially symmetric in this way. That's true in this instance of the experiment, in that the pattern you're getting is a radially symmetric wrinkle pattern, and not true in this one. So there's something truly different about these experiments, and well, I can't demo the second experiment, but I can show you videos. So let me show you that, okay? So we're going to do versions of the second experiment where you start with different shapes of sheets that are cut out of a curved sphere, and see what happens. So this one is going to start out being so you can see the buoyancy force is acting to pull it down, and you can see the wrinkle pattern emerge. So this one was cut out of a sphere, so it looked like a leaf cut out of a sphere, and you can see that it's very slowly finding an equilibrium, so it stops moving. You can see some wrinkles reconfiguring, and it finds this beautiful pattern, right? Okay, so we can redo this experiment with lots of different original shapes. It's easy to tell what the original shape was after the end of the experiment, because then it's flat and you can see what the shape looks like. So this one is the same as the previous experiment, which was a leaf cut out of a sphere, except for that the leaf is much wider. It's a much fatter leaf. And because of that, you can see, now they're going in and poking it to make sure that it's found this energy minimum state. You can see that something different happens. The pattern sort of, the leaf splits into sub-leaves, let's say, and splits up into different sections, each one finding its own wrinkle pattern. Okay, so that's interesting. Let's run one more video. All right. This one is going to show you a couple triangles. These are very bad contact lenses. So these are triangles that are cut out of a sphere, and then they're going to assume their rest configurations. And But now something very interesting happens. You see that there are these sort of smaller triangles found inside the larger ones where the wrinkles find those smaller triangles. They arrange themselves in this way. The wrinkles are not emerging perpendicularly from the boundary. So this is starting out curved and being stamped flat versus the other direction. All right, so let me go back to my slides now. Okay. Okay, good. So I want to tell you in the time that I have remaining all about that experiment and all about the mathematical analysis that I've been doing on it. So these are top views of the end state of the experiments that I just demoed by video. This one started out, you cut an equilateral triangle out of a sphere, and then you lay it flat, and it finds the inside triangle like this, right? This one starts out as a square cut out of a sphere, and then it finds a diamond inside of it. This one starts out as a hexagon, and it finds another hexagon inside of it. This one starts out as half of a ping pong ball, and it doesn't know which way to put the wrinkles. This is the leaf one that we started out with. This one started out as, you could say it's an ellipse. You could say it's an ellipse cut out of a sphere, if you wish, or a leaf cut out of a sphere, and all the wrinkles are parallel to each other, and this one is the leaf that's too fat, so it does something else. This one is a particular favorite of mine. I like to call it the envelope shape. It started out a rectangle cut out of the sphere, and it sort of divided up into this funny arrangement of wrinkles. Okay, all of these experiments are conducted at thicknesses at around around 50 micrometers. So let's go to the really thin sheets. So if you change the thickness of the sheets by several orders of magnitude thinner and ask a different experimental group to do the experiments that is able to do that, you get these results. And I just want to contrast those with the ones I just showed you. So if I take a thick hexagon cut out of a sphere, I get this sort of nice ordered wrinkle pattern. If I take the vanishing thickness limit, it splits into a disordered core, which is crumpled and doesn't know which way to go, and an ordered, you can barely see it, ordered wrinkled exterior of that core, which remembers how it was wrinkling in the previous thick configuration. And that's sort of generic. You take a triangle that looks like this nice ordered wrinkled pattern at thicknesses of micrometers, and you take it to about 100 nanometer thickness, and you get this pattern instead, where you see that the wrinkles on the three exterior triangles have been remembered, and something else is happening on the inside. This picture is actually very rare, experimentally rare. The typical picture is that on the inside you have some kind of disordered wrinkle pattern that looks like this, or frustrated crumpling pattern, or something else entirely that we don't quite understand. Okay. The resolution for the disk is that the disk here is just too symmetric. It doesn't know which way to put the wrinkles. So if you break the symmetry by cutting a wedge out of the sphere, it organizes the wrinkles in that way. Or if you break the symmetry by making the sphere into an ellipse, it organizes the wrinkles in that way. The sign of the curvature matters. If you take a lens, which is sphere-shaped, and you place it on water, you get all these patterns we just talked about. If you do the reverse experiment, and these are simulations, where you cut out all of these shapes from a saddle, like a horse's, you can picture a horse's saddle, you get wrinkles that do something completely different. That's like the demo that I was doing. So in the 4 minutes that I have left, I just want to tell you that we've figured out how this all works, actually. So there's a set of rules that you could teach anybody, and these rules tell you how to draw the wrinkles in every single one of these experiments. So let's start. These ones are easier to explain. So this one started out as a saddle shape, and usually when I teach math, there's chalk laying around. I just want to draw a saddle so that we can see what that looks like. So these ones started out from a shape that looks like this, and then you cut your choice of of triangle or whatever out of it, and you cut that out and you lay it down on the water. The rule for all of these pictures is that the wrinkles vanish at what's called the cut locus, which is an old geometric concept that asks to find the places in the sheet where if you were to try, let's say you stand on the green line, you stand there, and you want to exit the domain as quickly as possible by walking, running to the boundary as quickly as possible. So look, the wrinkles are telling you how to run. So if you're in any of the parts that are outside of the green segments, you follow the wrinkles, and that gets you out of the domain as quickly as possible. Straight line exit path. But if you're on the green line, you have many choices. You can go to the left or to the right. Once you make a choice, you have the path of fastest escape. And this is what the wrinkles do for negatively curved sheets. So wrinkles run perpendicularly to the boundary always. They vanish at the cut locus. The pattern is fully determined. For positively curved sheets, wrinkles vanish at the boundary rather than at the cut locus. They run parallel to something that I'd like to call contact polygons. So this is actually more difficult to explain. So I'm going to try to do it in 2 steps. Step 1, fit circles into your domain. So this one, I've fit the largest circle into the domain that I could possibly draw. This one, I fit the largest circle into the domain that I could possibly draw. This one, there's a whole family of largest circles. So I've chosen the left one and the right one for reasons that I don't have time to go into. And as soon as you do that, you can replace the circles with polygons where you line up the points of contact of those circles with the boundary. These are called contact polygons. And that's where the disorder happens and outside of which it's ordered. So there's this simple geometric construction that works for all of these cases. The pattern's not fully determined. Something funny is happening on the inside. If you chase these ideas down, you can even predict the amplitude of wrinkling. I have very little time remaining, so let me just say that this formula was something that came out of that mathematical analysis, which gives you the green prediction, and the simulation is showing you a perfect match. That same formula matches at many different places in the sheet all at once, so I think we're onto something here. And so in the time that I have left, I just want to make a few concluding remarks. I showed you a collection of experiments that came from engineering and physics that I like to think about every day. And they all have geometry questions hidden inside of them. Inscribing the largest circle, finding the cut locus, tiling the sphere in the best possible way. But they all come from the physics of thin elastic sheets, and I think this is a great subject to continue thinking about for many years to come. So let me just leave it there and thank my collaborators who generously provided the experimental photographs that I showed you in the last part of the talk from Syracuse and University of Pennsylvania. And as promised, this is where I got all of those beautiful pictures from. So thank you for your attention.